Hello everyone, welcome to this week's class, Analog Synth Cats in Space, which also happens to be my favorite Instagram account. I recommend everyone follow it. It is amazing, and all the photos and images of cats on synthesizers you're going to see during this lecture are from them. Shout out. Now, what we're going to do tonight is look at a synthesizer, and then we're going to construct that synthesizer ourselves a little bit later on using a piece of software called Tinkercad. We're going to learn more about the relationship that resistors and capacitors have in common by first taking a deeper dive down into capacitors and then looking at how they relate to resistors and the RC circuit. Let's jump right in. Let's take a quick look at Tinkercad. Tinkercad is a wonderful piece of software from Autodesk. If you need to create an Autodesk account, now would be a good moment to do that. After you've done that and logged in, you'll find yourself at this page. Tinkercad can do several really interesting things. It can do 3D design, it can do circuits, you can create code in it. There are many options and lessons, and I encourage you to explore. Tonight, we're going to look particularly at the circuits functionality. Go over to the Circuits tab, and I'm going to show you first what we're going to build. It's this Analog Synth Cat in Space circuit, which is credited to Nicholas Collins and can be found in his book Handmade Electronics originally. I'm going to go ahead and start the simulation. This effectively will turn this circuit on. So as you could see in that short demonstration, when I turned the knob on the resistor, I changed the pitch of the tone, and that has to do with how fast the capacitor attached to the oscillator, this chip right here, is decharging. And that relationship is what we're going to explore in tonight's lecture, on top of how to use Tinkercad and a general introduction. Let's go ahead, and since we're in Tinkercad, start with Tinkercad. I'm going to go back to where I was earlier and simply click Create New Circuit. Tinkercad automatically saves your work, so don't have any panics if you can't find what you're looking for. Also, a really great thing to know is Tinkercad has pre-built circuit assemblies. I'm going to just start off with the breadboard assembly here to give you a sense of how simple it is to get an Arduino set up in Tinkercad. That's it. You're done. Now let's go and get some basic parts. I'm going to go ahead and recreate the famous blink sketch from the Arduino help files. I'm going to start by finding a resistor, and I'm just going to search over here in the right-hand column. In the basic components, let me get out of here and do a search in all, and I have the resistor now. And I'm going to go ahead and put that on the ground side of where my LED will be, and I'm going to make it 440. I'm going to change this to ohms here to reset the value, and I'm going to make it 470 ohms. Then I'm going to go and get an LED. Let's use this one. And I am going to put it here. Then I'm going to connect by clicking on the breadboard, the LED, to pin, let's start with pin 13, which is the default Arduino pin, and it happens to be the default Blink Sketch code. I'm going to go ahead and click Start Simulation, and you'll see that immediately the LED starts to blink. The reason for this is Blink is loaded by default on this Arduino Uno sketch, and to see the code, all you have to do is click here. And note, you can look at it in block formats. It is set to the blink LED default LED, which is the LED that comes on your Arduino board. It is also connected to pin 13, and it comes on high, waits a second, then goes to low. If you stop the simulation and click here, you'll see that you can see the raw code, which is sometimes incredibly useful. If you would like to change the pin number or write code yourself, this is a great place to do it. Now let's say I wanted to run this code on my Arduino. All I'd have to do is click download code, and I would get an INO file that I could download right here. Notice the resistor and capacitor are on the start of the Arduino application, and there's a reason for that. We're going to explore it tonight. There you go. And if you want to learn more about the code blocks interface, I encourage you to take a look at it, but it is outside the scope of this tutorial. If you wish to export the board file for use in Eagle, it's just as simple as it was to export Arduino code. All you have to do is double click on it once it's downloaded, and it'll launch Autodesk Eagle. From here, you can route your board and send it to manufacturer. That was covered last week. All right, those are the Tinkercad basics. One more thing that's incredibly useful to know is if you make a mistake, you can simply click on the wire and hit delete. The same goes for a part, and if you want to change a part value, I've noticed a slight bug in Tinkercad. Click off the circuit board, slide the sketch, then reselect the part. See how it did that? And I don't know if that's a feature or a bug, but it's something I've noticed. And if it happens to you, just click on something else and come back. Eventually it'll pop back up there for you. And that's an easy way to deal with that. It also zooms in where you have your mouse, which is really different than like zooming if you're used to zooming in, say, a web page or whatever. So your mouse becomes the focal point of the zoom. It's like this in Eagle too, and it's something you need to get used to for working with these kinds of applications because it's a common implementation of the zoom functionality. All right, let's go back to looking at our slides. This is the moment where we're going to jump into looking at the components we're going to use tonight. So these are pictures of the components you saw on the first board I showed on Tinkercad, the synthesizer. There's several parts that we're going to use tonight, and they're all here. You're welcome to buy them. I hack a 1/4-inch jack in real life and solder the wires to the jack. That is a particular bit of functionality that we're not going to cover tonight. We're not going to cover soldering or live demos. But if you're interested in that, find me online and I'll help you out. So how does a speaker work? Speakers work in really unique and interesting ways, and they're very similar to the motors we saw. Motors have a copper coil that you induce a magnetic field around, and that magnetic field is essentially what causes your motor to spin, because you have a magnet, you have a copper coil, you get a magnetic field, good things. Speakers are very, very similar. The copper coil in this case is wrapped around the magnet, and when the coil's induced, let me repeat that. The copper coil is wrapped, separated from the magnet on the cone of the speaker here, and when the copper coil gets a charge around it, it induces a magnetic field, snapping it to the magnet, and that snap is actually what creates sound because it generates an audio wave, and I think this diagram is a really good explanation of that. In this way, we can kind of control how fast the magnet contracts using the voltage. And this lets us hear sound, which is a pretty interesting phenomenon. ExplainThatStuff.com is a wonderful website where you will find animated GIFs that demonstrate this concept. The capacitor we discussed before, but today we're going to go into in much more depth. We're going to look at different kinds of capacitors, fixed capacitors, polarized capacitors, and variable capacitors. Notice that some capacitors have pluses next to them, and just like LEDs, that indicates that they're polarized. And I mean that in the circuit diagram on the right-hand side of this side. They store charge, and without them, we would have so many more power flow problems in the modern world because voltage isn't always stable. For example, if you had a car with an electrical system without a capacitor, every time the speakers boomed and pulled power out of that circuit, the lights in the car would dim, and no one wants that. Capacitors measure charge in farads, and they use the exact same numbers that everything else like gigahertz and megabytes and all of that uses, only on a much smaller scale. So we're looking at picofarads, nanofarads, and microfarads in this case. As you can see, 1 picofarad is equivalent to 0.001 nanofarads. And in fact, you can sub a capacitor out that's got a value listed in picofarads to a value with nanofarads in your schematic, should you need to do that. It's a good emergency fix. If you need to convert because you have a capacitor that has all the values listed in nanofarads, a convenient converter is linked to these slides. Capacitors get energy exactly like a battery or a generator, and the device it stores it, so the capacitor holds that charge. If you move the voltage and isolate the capacitor, it will hang on to the electrical current inside of it. This is why a TV can absolutely shock you. Be very careful with that. Capacitors are known to have 2 metal plates, and they're separated by an insulator, which is called their dielectric. When the voltage drop happens across the circuit, what happens is the capacitor jumps in to fill that gap. And when the circuit and the capacitor are at the equal voltage, a capacitor is said to be fully charged. This is an example of a circuit with a dielectric in the center and the electrons flowing through it. As you can see, that gap there is essentially stopping the flow of current, but once the capacitor is fully charged, they'll jump across the dielectric and the circuit will be completely even if there's a power drop. So basically, if you look at the above sketch, when the voltage coming from the left-hand side of the negative side of the circuit is cut, it is enough to actually draw the negative electrons across the dielectric onto the other side of the circuit. And that's what this slide describes. And this is something really interesting to note here, that a capacitor, before it's fully charged, will essentially block the flow of current in a DC circuit. You can think of capacitors like cars at red lights. They take time to charge up, and then when you want to stop that flow of current, they take time to slow down. Capacitors have a very similar arc. And common uses are the flashes in a camera, a car stereo, and often radios. All radios really have capacitors inside them. Capacitors allow you to actually tune radios. And the ticks and clicks and stuff you get in a synthesizer are often as a result of having capacitors. And also they filter voltage. So if you've got a sensor that's extremely noisy and just spitting really high and low values, one of the things you can do is just slap a capacitor across power and ground, and that will equalize the flow of current in your circuit enough that it'll cut out some of that noise. Here's a simple charging and decharging circuit. As you can see, the switch indicates when the capacitor charges or decharges. In this case, one of the LEDs turns on if the capacitor is charging, and the other one turns on if it's discharging. So LED 1 is going to, let me take a quick look at this to make sure I don't mess it up. Yes, LED 1 will turn on when the switch is in the position that it's shown now, but if you flip the switch to the decharge side, the current will flow the other way through the circuit, and LED 2 will light up and LED 1 will go off. Capacitors and alternating current. So capacitors are really important in alternating current, but in DC circuits where they act like a block with alternating current, they can kind of act as a current level pass out. So when the alternating current flows back, the capacitor will jump in and fill that gap and essentially kind of give you direct current, even if you've got a alternating current on the other side, because the capacitor, if the value is large enough to cover the gap while the AC flows back, you've got a really great second power source, which is a really interesting and great way to use a capacitor. As the charge builds up on the capacitor plates themselves, it's not jumping across the dielectric. So it has to be fully charged before it goes across that jump, even if there's a power drop in the circuit. As the voltage rises from its negative peak, the capacitor again decharges through the AC source, but in the direction opposite of that of its original discharge. And it repeats the process, which is a really interesting way that capacitors keep light bulbs on in your house, even though they're plugged into an alternating current source. Capacitance is something we've played with in class. You've attached your capacitive touch sensors, and we've looked at tinfoil, we've looked at other objects which can hold charge, such as the human body. And the level of capacitance talks about how much charge something can hold. It depends on the surface area of the metal plates of the capacitor, the thickness of the dielectric, and the type of the material the dielectric is made out of, because dielectrics, much like resistors, are full of all kinds of different materials. As mentioned earlier, capacitors are measured in farads. This slide goes into a bit more depth, but also know that they have variance, just like resistors, and that's something to pay attention to. This is the common typical range of an array of capacitor types. So if you have a ceramic capacitor, it's going to have from 1 picofarads to 2.2 microfarads, and it's commonly going to be used for filtering and bypass. When you're working with voltage, it's referred to as the working voltage, or WV. The highest voltage that a manufacturer recommends placing across a capacitor safely is its working voltage. Most capacitors are between 16 and 35 volts. And if you build a circuit, it's really great to have a lot of headroom on it with the capacitor. And what I mean by this is it's okay to have a capacitor that's 10 or 15% more than your supply voltage. And the reason for that is if you end up with a larger voltage drop than you suspect, the capacitor has a bit more breathing room to help you out. Common dielectric material applications. Electroanalytic capacitors are often used to deal with signal frequencies like the synthesizer we're going to play with tonight, audio amplifiers. Mica capacitors are used in radios all the time. And if you match your capacitor to the one selected in your diagram, you're going to probably always be okay. But know that sometimes it's worth it to think to yourself, am I using the right capacitor for the application? And if you have an issue in your circuit, it might be something like wrong capacitor type. Some capacitors are polarized, just like LEDs. They'll have a longer leg. And you'll see a minus sign and a stripe going down the capacitor. And usually that's pointing towards a negative terminal. And that is something that you should pay attention to. Ceramic capacitors are often not polarized. Electrolytic capacitors are often polarized. You can, if you put too much voltage through a capacitor, blow it up. And if this happens, you can kiss some of your components goodbye because you just ran power in the wrong direction all over your circuit, and the capacitor might even explode. No fire will happen, generally, but there will be a nice loud pop, and your capacitor will spit its dielectric material all over your board. Reading the values. Often, if you see a ceramic capacitor, it's going to have the values printed on it, like 103 or 104. The way to decrypt what's going on there is it's 10 with 3 zeros. That's what 103 is going to be. It's 10 followed by 3 zeros. 104, 4 zeros. If it just has 2 values and no third value, it's telling you the value of the capacitor itself. So if you have to convert from picofarads to microfarads, just move the decimal point 6 places to the left. So capacitor marked with 103 has 10,000 picofarads or 0.1 microfarads. Varying capacitors. This is an awesome thing. You can have capacitors that vary. And quartz radios, which were a technology used during World War II, and they were these really cool homemade radios, and I recommend you look them up online. And if you're interested in a fun project one day, build one for yourself. But these crystal radios have variable capacitors that allows them to tune the radio, and it's a really interesting and cool application. You can also mechanically control a capacitor by moving the metal plates, and there's special diodes that can act as variable capacitors out there, and they're known as Vactrols or varicaps. They're very powerful and good in synthesizer design. Microphones are very, very common. They're everywhere. You can find them all over the place, and they are an example of a variable capacitor at work. The cone of the microphone has the diaphragm around the mic is acting as a variable capacitor plate, and the sound fluctuations are making the diaphragm vibrate, and the variance of capacitance produces the voltage fluctuations that allows the microphone to detect sound. Here's some capacitor diagrams again, just to review. Non-polarized capacitors do not have a plus sign on one side. Polarized capacitors do. Variable capacitors, just like variable resistors, have an arrow running through them. Capacitors in parallel work in serial mathematically. So the total capacitance in a circuit with two capacitors is C1 plus C2. That's simple. In series, the relationship is relational. So C1 times C2 divided by C1 plus C2 will give you the capacitance. Now, this is where the magic happens, teaming up with resistors. If you put these two capabilities together, you can control how fast electrons fill into the capacitor and how fast those electrons empty out. It's really a fun way to control the speed and flow of electricity through a capacitor. And this dynamic duo is so popular. In fact, it's called RC circuits. Here is an example of a RC circuit at work. And when you close the switch, the current starts to flow and charge when you close the switch, the current starts to flow and it charges up the capacitor plates. Ohm's law tells you that charging current, I, is determined by the voltage across the resistor and the value of the resistor. So I equals the voltage across the resistor divided by R. And because the voltage drop equals the voltage rise around the circuit, you know that the resistor voltage is the difference between the supply voltage and the capacitor voltage. So this mathematic equation will work for you. Voltage across the resistor equals the supply voltage minus the capacitor voltage. Initially, because the capacitor voltage is at 0, the resistor voltage is equal to the supply voltage at the very, very start. But as the capacitor begins to charge, it develops a voltage. So the resistor voltage begins to fall, which in turn reduces the charging current. The capacitor continues to charge, but at a slower rate until the charging has stopped. As the voltage across the capacitor continues to increase, the voltage across the resistor continues to decrease, And so the current continues to decrease. When a capacitor is fully charged, the capacitor will, when the capacitor is fully charged, current stops flowing, and the voltage drop across the resistor is 0, and the voltage drop across the capacitor is equal to the supply voltage. So basically, the voltage across the resistor and the voltage across the capacitor change places as the capacitor itself charges. So how fast the capacitor charges and discharges depends on the resistance of the capacitance of the resistance and capacitance of the RC circuit. The larger the resistance, the slower it takes to charge the capacitor. The smaller the resistance, the faster the capacitor charges. And this impacts our oscillator that we see in the next diagram. The larger the resistance, the lower the pitch, because the longer the waveform frequency will be. To calculate the time it takes for a capacitor to charge, you just go, the time is going to be the resistance times the capacitance. If you replace a power supply with a wire, by pressing a button, as in this circuit, it will decharge its charge. So this will effectively decharge the capacitor whenever you push the button. Initially, because the capacitor is fully charged in the circuit, the voltage drop is, let me say that again. Because the capacitor is fully charged at this point, the voltage is initially equal to the supply, right? So that makes sense. Your capacitor is fully charged. If you have a 5-volt capacitor, it is right now, right when you press that switch, 5 volts. But as it's going to decharge, the voltage is going to drop. Fully decharged, the capacitor will stop all power flowing. And you see this when you unplug a laptop or something with a capacitor inside of it out from the wall and the LED on it stays lit for a few seconds. It's because the capacitor is decharging. This relationship can be graphed, and this is an example of that. As the capacitor starts to charge up, it follows this graph. Once it reaches the supply voltage, it'll hang on to it. When the supply voltage is cut, the capacitor will decharge. Much of this description is taken from a brilliant book that I love called Electronic for Dummies, and you can go buy it. I encourage it. She's fantastic. The book taught me a lot, and if you're interested in what you can do with electronics beyond Arduino, it is a fantastic read. So tonight we're going to look at oscillators, or Schmidt triggers, as they're called. Basically, when you apply voltage above a certain threshold in an oscillator, it flips the state from off to on. So you can imagine that as you charge a capacitor, this is going to impact this, right? So if we put a capacitor here on pin 1, it'll charge up, and once it gets to its maximum charge, it'll flip that oscillator on, and the capacitor will drain out, and the oscillator will go off, and you'll get this on and off and on and off. This is the package we're going to be working with tonight, but note this is a symbolic schematic graph. This does not match the pins on the data sheet. This is really important to bear in mind because on IC packages, that number 8 pin that's flipped on, looks like it's on the other side of the switch there, is actually your ground. And 8 means the pin that looks like 9 on the IC. It got me the first time I tried to hook this up, and I'm just throwing it in tonight as a warning. This is one of those moments where ground is inferred. And we talked about this maybe the first or second week of class. Often ground in a circuit is inferred. And here you'll see that it looks like it's on 7, which is good to know. It's on 8, the package we're going to look at tonight, unless I'm completely unable to count pins, which is also entirely possible. This might be a 14-pin IC, in which case I'm just remembering 8 and 14 from working with 16-pin ICs. That actually, now that I think about it, is very likely if I look at this graph. If I look at 7 here, it seems to state that is ground quite clearly. Oh, Phoenix, you are not infallible. How does all of this make sound? I bet you can think about it, right? So the frequency of the oscillator is controlled by the capacitor and the resistor. The capacitor sets the pitch range, and the resistor sets the frequency at which that waveform is created. A 0.1 microfarad capacitor is a high frequency because there's not a whole lot of charge there. It's going to go on and off and on and off and on and off and on and off. A 10 microfarad capacitor holds a lot of charge, so it can take longer to decharge. You get a low frequency. These are the symbols for capacitors, resistors, junctions, buttons, and just a nice review in case you have forgotten what any of these mean before we move forward and look at the next diagram. Now sound. Ba-da-ba-ba-ba. Here is the cover of Nicholas Collins's excellent book. It is so old, a DVD is included, and I have had it on good authority that he's releasing a second version. I encourage everyone to watch the video that is linked on this week's class on Moodle. This is Casper Electronics demonstrating to you how this circuit works. This is the picture from Nicholas Collins's book. Notice here that the ground is attached to the capacitor, which in turn is attached to the oscillator. Also, that the pin of the variable resistor is attached, and it's attached across here, the resistor. So it's going into pin 1 and 2 here across that oscillator. I have to count. Now I know it's 7. 4, 5. Oh, it is 7. Oh, Phoenix, too many 16 pin ICs in your life. Good to know. I've just been hooking it up that way out of sheer habit. The bottom pin on the left side of your IC package, always ground. The top right pin, always power. It doesn't matter how many feet that little bug has. 4, 14, 18, tons and tons. They'll all follow this convention. Notice here our power supply is coming from a battery, and our speaker is actually plugged into the output side of the oscillator, which makes a whole lot of sense, right? And ground. You need to connect it to ground. This is the kind of crazy situation you can get yourself into. You can hook up so many beautiful, beautiful, beautiful parts and just release the kraken of awesome. It's a fantastic thing. If your curiosity takes you to this kind of level of exploration, I encourage it. Notice that you don't see a speaker here, and that's because people are just plugging in at different points and listening to different sounds, building up sound. It's a great way to make music. This is a kit I created for Duet Kits, which is my friend Helen's company. I showed her how to build this circuit initially, and she sold them as kits, and we collaborated on it. And she took this workshop originally several years ago, and now she's gone on to make so many amazing instruments. A video that she made of this circuit is here, and it's also on the Moodle. Here are 3 possible configurations from Nicholas Collins and Casper Electronics. You can control the resistor with a pot, with a light, dependent resistor, or even 2 points across your hand, because we learned that you have resistance and can store charge. Here's a simple pitch modulation. Here's what it looks like if you sync oscillators. For those of you interested in taking it further, I would encourage this second circuit in Tinkercad. So for the next steps, you can jump over, watch that video, and we're going to look at it now in Tinkercad. Tinkercad, dun dun dun. I'm going to go back to my root folder here, and I'm going to go and get Analog Synthcats in Space and tinker it. All right, hopefully this circuit now makes a whole lot more sense. There are two little LEDs in here that are essentially just letting me see how fast the pulse wave is. If I come here, you'll see you can start seeing them flickering. Very fun, right? And you'll notice that this capacitor, the stripe, as I promised, this is the negative side, is going to ground. The positive side is going to the first pin on the oscillator. Then, exactly as in Nicholas Collins' schematic, one side of our pot, as we know, the wiper is here, right? So as the wiper goes across the electronic, as the wiper goes across the capacitor, right, and gets closer to this point, there'll be less resistance because it'll just be that much, right? So this second part, this part that can control so if the wiper is all the way over here and then this is all the way over there, this resistor across this bit of the circuit is going to be pretty high. So that's good to know. And the second half of it is going across here, and that variance is what we're hearing in the pitch change right now. You can also, I'm going to do a thing really quick where I just play with. So that's that capacitor at maximum pitch. What happens if I come over here and grab this and change this? I'm going to change it down to 10. Do I have that option? Yeah, nanofarads. All right, let's do this. Very high pitched indeed. And what if I make it microfarads? Very slow, very slow. And you now see the LEDs flashing. How about 100? And that will, of course, that relationship will change. How fast that's going. Absolutely. Hear it speed up? Uh-oh. There it is. So here, they're really close together, right? Very small resistor. Very big resistor. Sometimes the simulation is a bit slow. And if that happens, just stop it, start it again. It can only run as fast as the browser will let it, unfortunately. So this circuit, not perfect when it comes to simulation, but it's a good replacement for A, looking at a schematic on a breadboard versus a schematic drawing, and B, building something for free for testing. This will save you a lot of money because you can test your parts ahead of time. And I just found the hex Schmidt trigger by searching for hex in the components. That's important to know, not the number. Note the number on this Schmidt trigger is different than the number in our slides. They're electronically the same. One is made by Texas Instruments, has a different number. That's all. Awesome. Then you can also play with the resistance. There's that bug again. There we go. So what happens to my circuit if I make my resistance, instead of 550 kiloohms, 100 kiloohms? What if I make it way smaller? That means it does not like it. Nothing happening. Very slow here. So, right? Notice these LEDs are flipped, and one side has a resistor going to ground and the other side has a resistor going to power. Go back and look at the slides and try and guess what I'm doing here. One is showing you when the capacitor is charging. The other one discharging. Charge, discharge. Let's speed this up. right? Very small resistance, very fast charge. All right, I hope that helps make sense. Notice that Tinkercad has a power supply. You can find this by searching for power. And I have it set to 5 volts. I encourage looking at 5. If you look at 9, you're going to need different parts. And the schematics in the book often use a 9 volt. So know that that's a thing. Also, you can change how much of the oscillator you're seeing. So 100, 1000. Sometimes it takes a sec. But if you change this, you'll see the waveform totally differently. Maybe. If Tinkercad likes you and Chrome likes you. There we go. So it's not as good as a regular scope that you might have on your bench, but it gives you a good idea. Getting pretty good rhythms. All right, that's it for tonight. Enjoy. Build this circuit for yourself. Have a good time. Play with the capacitor values. Play with the resistance values. Go over the notes and try and make this make sense for yourself. To find this part, just search for speaker or sound. Whoops. Let me stop simulation and go back. If this happens, you can just close code view and search for, I think it's just, you may have to search for piezo. Let's see. There it is. So you're going to need to search for piezo to find this lovely part instead of speaker. So know that going in. All right, that's it for tonight, and I'll see you next week.